record on his computer. Good afternoon, everybody. I hope we solve the issue of this machine, which is new and with new hardware and old Linux kernel. Life is challenge. Okay, but let's get started. So what was the last time what did we discuss last week? Well, actually it wasn't last week, it was a couple of weeks back. So let's refresh a little bit what we have been doing so far. Just to refresh. So I hope this works. Yes. Okay, so we said we need, for some private data analysis, we need something randomized. Okay, so the text anonymization, which arbitrary decisions, versus something where we have randomness, which you can undo, so there's probable privacy. And we talk about the trusted curator privacy with the counting queries, and we kind of end up with this epsilon zero pure differential privacy thing. So how many people are in there, some numeric queries and stuff like that. And we also showed that for protecting privacy in the setup, one of the natural mechanisms was this Laplace mechanism. So basically taking a random value from a Laplace and adding it to the true value which we want to answer in the data set, right? And we talk about numeric queries and this L1 sensitivity. Then we talk about some any range queries, so something which could be discrete. We had this example with the cities and choosing among a couple of options, also in differential private manner. And we talk about this exponential mechanism, but all of them were so far the epsilon zero, okay? And we talked about local differential privacy last time, where we said, well, you know, nothing is preventing us to make the database as small as one person, and two databases are different if these persons are different. So it's still, everything we had so far will work. So what we are going to do today is a thing called approximate differential privacy. And we're gonna relax a little bit of our kind of strength of privacy we're having so far, okay? So, but we have to start with one thing, and maybe it will be a little bit of probability theory in there or statistics or something, but it should reveal something that you already know from other fields, that it could be useful here as well. So we have this example of, I mean, of course, recall, you don't have to recall lecture 3 slide exactly 34. But I just look it up, it was there. So you can refresh then if you look back. Then we said that, just move this away. We said that so we had two neighboring data sets, and we said that for these two, the probability distribution, so it was for a Laplace distribution. And we said that the ratio of any two neighboring data sets is limited, right? So the maximum we could kind of reach of the ratio of whether this comes from one data set or the other data set, which differ in one person, the ratio is bounded. And in this case was exactly Euler's number, 2.7. And we did it for a couple of different scales of the Laplace mechanism or the Laplace distribution to see, like, well, actually by controlling the size of the noise or the width of the noise, we can control how much we're bounding this from above, right? So this brought us to the epsilon zero differential privacy, where we saw, like, well, it can't be any larger for given epsilon and given mechanism. We are always bounded here by some maximum number, this privacy budget. Okay. And this is exactly what I was referring to. So, the scale kind of control the strength of privacy. And we saw in the Laplace mechanism for this counting query that if we had larger scale, so more noise, it pushes down how much information we learn from one database as opposed to the other database, okay? So I hope it does ring a bell a little bit. So we had this before. So and this led us to kind of define the epsilon zero differential privacy. So, and we formalize this definition of epsilon zero differential privacy or pure differential privacy as bounding the ratio of two randomized things. So this could be, for example, the Laplace mechanism or Laplace distribution, that any output from over one database versus the output over any neighboring database, and the neighboring data sets, we discussed it a little bit, so could be different, they differ in one row, either removing or adding, or they just differ in the contact node or the person actually which they are kind of correspond to. The ratio of then is bounded by e to the power of epsilon. And this is controlling the privacy budget, it's controlling the strength of the privacy. So far, so good. And we showed a couple of mechanisms which actually fulfill this criteria. And we actually made a couple of proofs in the exercises for the Laplace mechanism, for the exponential mechanism. So far, so good. So this is a refresher. I hope everybody's a little less, more or less on board. So we were using this sort of notion of privacy loss. So we bounded by our privacy loss by epsilon, and here just a little bit of algebraic operations. So by dividing by this right hand side and taking logarithm, we said that this thing is never more than this privacy budget. So this is the worst case scenario that can happen when we do something about counting people in the database, choosing one option over the other. If the mechanism is epsilon zero differential private, this must hold. So what are MDs and MD primes? So these are I would say these are random variables, because this is like the private mechanism, and this is randomized. So somewhere in the mechanism, there is a random variable, right? And we saw it before. For example, in the Laplace mechanism, we would say, yeah, I mean, in order to output some number, we take the true value and add some random number from Laplace noise. So we would say, take the value and then draw some value from Laplace, which is parameterized by the scale. Maybe we would pick this value, so we would basically report this value as a private thing. So, but there was some random variable in there, and it was Laplacian random variable. The randomized response we are talking. Okay, randomized response, exactly. So the local differential privacy is randomized response. We took basically well, not a coin toss, because coin is like 50-50, but some sort of biased coin. So we are drawing from Bernoulli variable. Okay, so this is a function of a random variable, or there is some random variable, so drawing from random variable in there. And we know that since this is a function of a random variable, it is also a random variable, right? So random variable, if you go deeper into what a random variable is, there's multiple definitions, and depending on how tricky, how deep you want to go, you end up with measure theory at the end. But we thought, we said like we're not going to go that deep in the rabbit hole. But if you have a random variable and have a function of a random variable, it's again going to be a random variable. So the distribution will change in a way. I think I have an example on the next. Oh wait, I will have example later on. But let me just finish this sort of reasoning about this random variable. So we said, well, this is this is bounded, and there are some probability variable, some random variables in there. So since the mechanism MD is random variable, okay, so this is a random variable, and the whole thing is a function of MD. This is again a random variable. Oh, good. Okay, cool. Yeah, this is nothing else than a function of a random variable, which is a very complicated function because we're taking the probability of this and stuff like that. At the end of the day, there is some random variable in there, some maybe Laplace or coin throwing, and you add ratios, probability of this, and logarithm on top of that. At the end of the day, it's a probability variable, and it's a random variable. The question, I mean, here, this is the key point, so you might refresh that. Random variables, they can be pushed through functions, right? So if X is a random variable, then if we push it through some function, it's also a random variable. And in our case, the function, which I call here G, it's complicated, even including the probability of X and stuff like that. But you know this already from other places. And I guess on the next slide, I have a couple of examples why you know this. But any questions so far? That's important. Yes.
There's the border around your camera that you speak, and that in the microphone there's you can see when you're talking.
Okay. It's possible that I'm not recording like audio, or are you certain? I see. Okay, well, it didn't complain. I mean, before it complained, but now, okay, let me check that. How can I How can I check that? That's a good question. I don't think I can check that now without ending the meeting and oh, that's an interesting question. Okay, so how okay.
Share the link in the Discord again.
Yeah, I'm gonna do this thing. Okay, so recording. And yes, I know I'm sharing a screen. How the heck I just hide this?
The arrow with the sharing your screen.
Yeah.
The bottom one is the bottom.
This one? Oh, here. Yeah. Okay. Good. Okay. So coming back. Yeah, this away. Okay, I hate this. I hate this is like I hate this Linux. Okay, well, I hated Mac as well. So again, so this is a function of a random variables again, random variable. Okay, what is a distribution? Who knows? Could be anything. I mean, if you have if this were a Gaussian, what happens if this function would be, I don't know, multiplied by 2? I guess if you multiply by 2 a Gaussian, it will just get like, wider, but it will be still Gaussian. If this were something else, who knows? Okay, so in general, like you can transform random variable into some other random variable by function. The big question is like, how is the distribution changing and can you do something about it? Okay. So, and let me just close this here again. So we don't, I don't know if it's like that. Go away, go away. Yeah, you already know like functions of random variables that have similar form where, there is a function of random variable which also is taking probability. So, okay, first question, expectation of X. Oh, so X is a random variable. So you need to do like expectation of X. How do you do expectations? It's a discrete random variable, okay? How do you compute expectation or a mean? So X is a random variable, okay? So random variable. How do you get a expectation of this random variable?
Range.
Yes?
Range.
There's some range, okay? I think it's like weighted average. Do they call it like that? Yeah, okay. Yes.
The sum of all values of X multiplied with the probability.
Multiply with the probability. So you take all X in the range of X, and you take the value times probability that this is it. Oh, okay. I think I had it on the slide exactly like that. Okay. So this is the definition of expectation and it's weighted average. Okay. Well, you see, oh, actually it's a function, it's a sum. And in this function, we have the value of this random variable as well as the probability of this random variable. Okay. So, it's a little bit complicated in this one, of course. I mean, sorry, this one is a little bit complicated, but then we have a random variable and transform it to something else, like a value. Okay, cool. So this is a real number, but not a function. Well, anyway, but we have something like entropy. So again, in this entropy, we again take, it's an expectation. Now we have to think like, expectation with respect to what? Well, this is simple. We still have one random variable here, which is X. So we kind of assume, well, yeah, this is with respect to X. And then we know how to do expectations of a function. So this is a function of random variable, right? Logarithm 1 over P probability of X being equal to X. And you see, I'm getting sloppy here because this is all the time you see like it. I mean, properly, we might write something like that, but just ignore this and just write Px. And then you can compute the entropy of random variable X. And again, it's just a sum of that. Okay, cool. So, there's no magic. I mean, you've seen this before, most likely. There's another one. Oh, now we have two random variables. Okay, so KL divergence between X and Y, and we're assuming they have the same range, okay? So this is a function of, wait a second, this is a function expectation of a Px and Py. Okay, now this is a function of two random variables. But how is it distributed? Because we need to compute the expectation. So this here, we're taking the assumption, and this is really assumption that is distributed. This whole thing is distributed according to X. So which means then, okay, here we implicitly assume exactly this function of X. and it's therefore distributed according to X, which means we can compute the expectation by just applying the formula we've seen before. So we just say, or for X in range X, we just multiply the probability of X by the function, and the function was this logarithm of these two things. Oh yeah, this is how you know KL divergence. So it's a function of random variable, and for the function of random variable, you can do stuff like expectation. Okay, so this is why this shouldn't be, surprising. This is a random variable which is distributed according to MD. And why MD is a random variable? Because it's a privacy mechanism, and there is some randomness in there, either Laplace distribution, Bernoulli distribution, some exponential distribution, whatever. So it's a random variable, it's a function of random variable, and the whole thing is a function of random variable. Okay? Doesn't make sense. It's sort of like reasoning where, we are just building from very simple random variables. Why the heck are we doing this? Is a good question. So, okay, so because we want to end up with something called privacy loss random variable. So MD and MD prime are these mechanisms, and these are also random variables because there's some randomness in the process. So then we define the privacy loss random variable with this fancy L, and we are saying, oh yeah, this is parameterized with these two random variables, the MD, M over D and M over D prime, as a logarithm of these two things. And it's distributed by drawing T according to this. Okay, so this is definition. But the reasoning behind is like, it's not different from how we define, for example, entropy, KL divergence. And by the way, there is something like beneath, there is some correspondence to divergences and privacy loss random variable. We don't go there, but there is something about it. So that's why the privacy loss random variable makes sense. And for example, now you should be, now you should know how to compute the expectation of this privacy loss random variable. We're not going to be using the expectation of this privacy loss random variable, but just by applying this sort of reasoning, you should be able to do expectation of this thing if you need to. Expectation is not interesting because expectation is something on average. In privacy, we are interested in the worst case scenario, which is the maximum. Okay. So this is how we end up with privacy loss random variable. I really hope it makes sense. And maybe I might have skipped something that kind of you say like, what this is about. So if this is the case, let me know. Okay. Well, you might not have questions now, and that's great. You might have questions later about this, and then let me know. Just ask, because it might not be like that straightforward. Why are we doing this? But we have privacy loss random variable, which is this logarithm, and it's distributed according to, to the denominator, to this random variable. Okay. Good. And I think it's time for showing an example of a privacy loss random variable. So again, this is again the definition from the previous slide. And for example, how would this distribution? Okay, so there is some random variable, and the random variable have distributions, right? This is what matters. How is the random variable distributed? Is it Gaussian? Is it Laplace? Is it something like very weird? What are the probabilities? So the question is, how would the distribution of this privacy loss random variable, for example, would look like for the Laplace mechanism? So here again, I reused the example from the previous lectures where we had, there was like a counting query, so single output, single real value output. And it was like, oh, how many people in the database have, condition A? And the true answer for one database was 50, and 51. And if you removed one person, like the neighboring data set would be 50. Okay, so we would have two Laplace distributions. So one would be corresponding to the true one, and this would be corresponding to this one, I guess. And now we just try to apply this formula and see how the privacy loss random variable will look like. It will be some distribution. So who thinks, okay, let me see. So who thinks that this distribution of this privacy loss random variable will be nice? Something like, I don't know, how could do, like something like Laplacian, or B, ugly, something like very, very weird. Just a poll. So just a guess. How is this going to be distributed? We have, I mean, you don't have to, I'm just curious, like, what do you think? Is it going to be nice or ugly? So who is for nice? Okay, one. Who's for ugly? At least 2, 3. Yeah, I'm sorry, it's going to be very ugly. Like something very unexpected, okay? I did this empirically, basically by running this in NumPy and just plotting. So you can do the computations and see how exactly this is a histogram, okay? So this is not exactly like analytical formula, but you could do the analytical formula if you really want. And this is interesting. So the privacy loss random variable is defined like that, and distributed according to this one, which is this true distribution. It's very weird one. So it's yeah, okay. So this is the value of the privacy loss random variable, and this is just the histogram or density. So basically, like how likely the probability loss random variable, privacy loss random variable will be ending up. What is really interesting here is that this Laplace mechanism was with was parameterized for epsilon of 1. And here we see again that the maximum value that the privacy loss random variable takes is what? Is 1. Okay. There is nothing here. There's nothing. Okay. Okay. Yeah, cool. That's by design, but we can see it right now. So the privacy loss random variable is, the privacy loss will be something in between, most likely here, then maybe here, and maybe sometimes here, but never bigger than what we said. Okay, so this is the hard limit. Like you cannot really, so this distribution, it will never go beyond 1, and this actually never go beyond here. So the distribution is really bounded by this epsilon. Okay, this is cool. Okay, so remember this picture. This is for, and this is very ugly distribution. I don't know. I mean, it doesn't have a name. It's just you take 2 Laplacians and squeeze it through this logarithm and the ratio, and again distribute again 1 Laplacian. This is what you get. So it is very ugly for Laplacians, but it's bounded by this value. Okay. Any questions? All right. So my question would be, what if epsilon were 2? How would this picture change? If we have, if we say the Laplace mechanism is epsilon of maybe 2, how will it change? Just a sanity check. So will it go like more to the left and more to the right, right? Well, where will it stop? -2 and 2. So it will just more spread, but you never cross this kind of hard thing. All right. Yeah, I mean, somehow I thought it's going to be a course on natural language processing, like a module on natural language processing, and we're doing like basically differential privacy. Well, I don't know. I mean, as I said, like it's an experiment, so we should end up with language again. No worries, we'll get there. But this is something like it's not like super easy, the foundations. But anyway, we'll get somewhere. So the values of this privacy loss random variables are upper bounded by epsilon. This is epsilon 0 differential privacy. And this distribution, it demonstrates, it's not a proof. I mean, it's basically like shows like how it looks like, that the value of this random variable exceeds epsilon. So this would be the epsilon of 1. Exceeds epsilon is 0. Oh yeah, okay, well, we know it already. So the probability that we will end up here or somewhere here is 0. There's nothing, no mass here. So everything is between -1 and 1. In other words, and now it's getting kind of tricky, like why the heck are we doing this? But you will see later. So the probability that this will be less or equal, the absolute value will be less or equal than epsilon is 1, like always. Okay, cool. Yeah, so but this will lead us to something like maybe this is not necessary. Maybe this is super hard constraints, and maybe what if we have cases where sometimes we might have something here, just very not often, but sometimes we might violate this epsilon by a small amount. Why this could be useful? Well, I don't know, we're sacrificing, we're going to sacrifice privacy a little bit, but maybe we get better utility. So something which will help us to be more precise, like not so much noise. So what if we don't need to ensure this bound all the time? What if we allow it to exceed the epsilon with some small probability? So we would basically say, well, maybe this would be a little bit smaller, and maybe we can have it little bit here, maybe a little bit here, and then maybe here not anymore. So maybe it would stop here, and this will be 0 again. Okay, something like that. Redistribute a little bit the privacy loss to values which are bigger than epsilon, but not much. The question is like, well, how much is not much, and so on. Oh, we'll come to that later. But what if we do this? So we would change that this probability of not exceeding epsilon must be 1 into some small tiny little delta. So we this mass here, the overall mass would be some delta, some small probability. And we would say, well, yeah, okay, we can exceed this privacy loss bound by some delta. So basically these two are equivalent. It's saying, well, yeah, okay, the probability under the epsilon, here, the probability is not 1, like the whole kind of sum of those is not 1, but something smaller than 1, like maybe 0.9999. And the probability here could be 0.00001. Okay. Are these two are equivalent, right? Makes sense? Yeah, I'm actually not sure about these, whether this is like greater or equal or greater, because in some cases might not play an important role. So I believe this is correct, but it might have been like little bit on the boundary, you have to make decisions maybe. So I'm not like 100% sure about those. But in general, you would say, yeah, I mean, we can go here with a tiny little probability of delta. It should be a little bit than delta. And if delta is 0.1, so this should be smaller than this delta, where we will exceed this, okay? Good, okay, wow. Now let's formalize this, because it leads us to, finally, the approximate epsilon delta differential privacy. Oh, okay, so we had before, what we had? Epsilon 0. And now we will understand why the 0 was in there, because now we have the delta, and we, if x equals to 0, we get what we had before. So again, a mechanism is epsilon delta differential private if for two neighboring data sets, D and D prime, and in output, there is a guarantee. So this is the same that we had before, except for we're adding this tiny little delta to this equation. So we say, yeah, you know what? There is a chance that this won't hold, and this little chance is this delta. And if delta is 0, what do we get? I mean, we get this epsilon 0 differential privacy as you had before. This is the same. But now there is no 0, there is tiny little delta, and we don't have a pure differential privacy anymore, but we have it epsilon delta differential privacy, approximate differential privacy. Okay, so this is more like general definition. So what should we think about now the delta? I mean, do I have examples here? I hope so. Yeah, so now we might be asking like, oh yeah, okay. So we spend like 20 minutes talking about this privacy loss random variable where we had these kind of, bounds and things like that. And then we have this definition, but it looks looks different than this thing. So there's equivalence, there's a proof that these two things are equivalent to say. But this is very nasty proof. So if you really want to go into there, like it's 3 pages in this book I'm referring to, you can download it and have fun with random variables. But you don't have to do that. You can trust me on that, or trust the book, or trust the authors of that. But basically, it's saying that, well, this definition, which we know already, says that, oh yeah, if you're bound to privacy loss random variable, if you let it cross the bridge, so to say, like be, not fulfill the guarantees of epsilon by some small tiny little amount, this is the same as saying this definition. Okay, so these are equivalent. Why is this privacy loss random variable nice? Well, we will see later with the Gaussian. It will be very nice, but we're not there yet. Okay, so this is, if you should remember something from differential privacy, is maybe this definition of epsilon delta, right? So this is like, yeah. This is the definition. There is some little delta, and the rest is kind of, there is a factor which multiplies these two, basically bounds the ratio of seeing it from two different neighboring data sets. Okay, any questions so far? All right, good. Let's move on. Now, what does this delta do? Okay, so why? Is it good? Is it bad? Does it help us? Does it hurt us? Yeah, that's a good question. So we can find, I'm gonna showcase the two algorithms which shows that the delta is a very, very bad thing. So there are deltas that will kind of destroy everything. So the query would be, so okay, when bad things are really bad. So let's make an example. We have a query that says, we have a database of secrets and give me the database, give me all the rows. Why not? I mean, I can, this is a query. I'm asking like, yeah, give me your data set. So we have this example data set. I took it from the previous example. So, we have names and drug use and something which, nobody should really figure out. Not even for a single person, like the whole data set is a disaster. So nobody should know. And our goal is to have this algorithm epsilon delta DP. Okay, so we say, whoa, we have epsilon delta differential privacy. So this should protect privacy, right? Right? Oh, yeah. It should, but it can go wrong. So then what we will say is that with probability 1 minus delta, so very high probability, most likely, so maybe like 99% probability, we will return completely random table. We just return, this is like a fake data. It's completely random, okay? This was the original, Elise, Bob, Charlie, and so on. And with very small probability, very high probability, we just make it up and give it back to you. So it's random, completely random. And since the output is completely random, there would be no difference in outputs of any neighboring data sets D and D prime, because we just basically ignore D and D prime completely. So whatever we do, whatever is in the data doesn't have any influence. So this is a perfectly private algorithm with epsilon 0. It's completely random. No epsilon eaten, nothing. It's random. Is it good? Well, no, it's pretty bad. I mean, for the utility, you learn nothing from that. It's just random. But that's, this is epsilon differential private now. Good. Second part, now with probability delta, this tiny little delta, we just return the original data set in full, like, oh, here's my database of patients. Okay. And this part of algorithm is basically purely deterministic because there is no randomness. There is no randomness. I will just give you the full data set. And then what would be the privacy loss here? Well, infinite. Why is it so? Well, if you take a D and D prime, so if you remove at least from the data set and D prime, you need to check that this will be, actually, if you remove D prime, this algorithm is never going to return D prime because this algorithm is always going to return D. So if you remove D prime, this possibility is never existing, which leads to this ratio of two neighboring data sets where one is something and the other is basically 0 because there is no probability. Oh, excuse me, D prime, yeah, exactly. Probability is, no, this is wrong. This should be like that, 0. Basically, the probability is 0 and you dividing by 0, you get infinite. So basically, makes sense like intuitively and even formally. If I give you the full data set, this is the worst case scenario, okay? So we have two parts, like with very high probability, I give you something random. With very small probability, I'll give you the original data set. This is the, kind of a very bad scenario, right? This is a summary. So with probability 1 minus delta, return completely random table, so epsilon is 0. So there is privacy losses. There's no privacy loss. And with small probability delta, I will give you full data set with infinite privacy loss. But our algorithm is epsilon differential, epsilon delta differential private. It is. And in fact, it's zero delta differential private because this holds, right? I mean, with with something smaller than delta, I can exceed epsilon. I exceeded I exceeded like in a very bad way. Like I exceeded like, it can't be any worse. Like I give you the full data set. But yeah, this holds. And if I'm larger than epsilon, I'm smaller than it, than epsilon, or the same, like there's no zero is there. Okay. So bad things happen with delta. So the delta should be very, very small, right? I mean, the chance that I'll give you the algorithm is stupid, but it just showcases that even if something is epsilon delta differential private and the delta is small, bad things can happen. So the delta should be super, super, super small. Like, I mean, we had this example here. Maybe this should be 0.1, but maybe it's too much because maybe what we had in this example that, okay, was the value of the privacy loss random variable. And in our example, we went to actually plus infinity almost, well, it was plus infinity. And then we kind of had this value. So we really went far, far, far away. I mean, as far as possible from what we would be guaranteeing. So that's maybe not not nice, but it's possible, right? We didn't say like how far should we get. We say like, well, we can be, we can cross the bridge here and go to these territories, but is it good or not? Well, in this case, it was pretty bad. So maybe the delta should be super small. Okay, cool. Let's do that. So extreme algorithm number 2. I don't want to leak the full table, but maybe just a few entries, few rows. So it's similar, like given database of secrets, give me a few rows verbatim. So this time I'm not asking you for like, oh, give me the full thing, but a few rows. And again, our goal is to have this algorithm epsilon delta dp or 0 delta dp. So epsilon delta dp where epsilon is 0. So how are we gonna do that? Well, okay, so I'm gonna iterate over all these n rows. So now we know there's n rows. And for each row independently, with small probability delta, I'm going to add the row to the output. Okay, so I'm saying, okay, well, Ellie's first row, then I throw the coin with very small delta. And if it comes heads, then I say, okay, I'm gonna put you to the output. Next row, okay, Bob, throw a coin with delta. Oh, yeah, okay. No, and so on. Okay, so I'm just selecting each of them independently with the random coin toss to output. Okay. So again, this has bad consequences. Maybe not that bad as before because I don't give you the full data set, but still I give you verbatim like a few people in there. So what is the probability that at least one person will be leaked? This probability will be proportional to delta times n, roughly, for some small deltas. Why exactly that? Well, the probability that a single person will not be leaked is 1 minus delta, and we have independent draws, so there's to the power of n, because these are independent, so n times 1 minus delta, and the whole thing 1 minus. That this is the probability that at least one will be leaked in the data set. So what does it mean? It's getting more practical now. Will you give me your data if I give you delta, which kind of the chance that you will be leaked is proportional to the number of people in there? Oh yeah, so now it's getting interesting. So we see that the delta has to do something with the number of instances or number of examples in the data. So we should take some measures and say some general recommendations. So if we are working with epsilon delta differential privacy, the delta should be much, much, much smaller than 1 over n. Okay, this is the general recommendation. So for example, if you have 1,000 instances in your database, so delta should be much, much smaller than 1 over 1,000. So even smaller. So typically, people are using deltas of 1 to 1 millionth, for example, and people call it like cryptographically small. So there is a very, 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 very small chance, like 1 in million or 1 in 10 millions or 1 in 100 millions, that this delta will happen. Okay. So then this algorithm would be okay, because the chances that actually one of those rows will be outputted is very, very, very small. It can happen, but it's small. Okay? So if there's something that you also maybe should remember for epsilon delta differential privacy, the delta must be very, very small. The question now is like, okay, so we had a pure differential privacy and there was no delta, so we didn't have to deal with this kind of second decision. I mean, the first decision was like, how big should my epsilon be? Yeah, it's a tough question. I mean, it depends. But it was fine. It was like one decision to take. Now we have epsilon delta differential privacy. How big the delta should be. So, okay, we have some guidance. It should be much smaller than 1 over size of the database or 1 over size of the database squared. So is it worth the effort now, like having two different kind of variables? Yes, because we have some better mechanism than the Laplace mechanism. We have a Gaussian mechanism. And the Gaussian mechanism is it has very nice properties, which will be super useful later on. It comes with weaker privacy because now the Gaussian mechanism, as we will see, is epsilon delta and not epsilon zero differential private, but it behaves very nicely. And many things in, like if you do any statistics or machine learning, many things are Gaussians, not Laplacians. Okay, so this will be interesting. Good. So let's move there. So if you remember the L1 sensitivity, what was the L1 sensitivity again? What was that? Anyone remembers the L1 sensitivity of query? So the L1 sensitivity of the query was the maximum difference. So we have function like numeric query. So I don't know, give me numbers, give me all the numbers in the, give me average income in the database. And the F1, L1 sensitivity of this function would be, if I remove one person from the database, how much will this, how much maximally will this change in? And we use the Manhattan distance. We use the L1 norm, right? So if you have two in L1, we have, let's say 2 points, like 2 vectors. So this is like in 2 dimensions. So we have here one vector and here another point. So the L1 distance was basically this, like the sum of on each dimension. Okay, so Manhattan distance or Texican distance. This was the L1 norm for 2 dimensions here. L2 norm is much more natural. It's basically the Euclidean distance. So Euclidean distance is this, right? Like Pythagorean theorems, Euclidean distance, you get the direct, like the shortest path in Euclidean space from between 2 points. And this is the same. So, I mean, if we have 2 neighboring data sets and apply the function on them, and we get a vector, because this function produces a vector, then we ask like, yeah, what is the minimum distance of these 2 points in Euclidean space? And we're using the Euclidean distance. Euclidean distance, exactly, L2 norm. Okay, any questions? Euclidean norm is always smaller than L1 norm, right? L2 is always smaller or equal to L1. L1 is same to L2 just in 1 dimension. If you have multiple dimensions, then L2 is smaller. Okay. This is interesting because if you remember the Laplace mechanism, we were adding noise, which was proportional to the sensitivity, to the L1 sensitivity. And if you have multiple dimensions with L1 sensitivity, you would need much more noise because of this. Because this is always larger than, the L1 is always bigger than L2. Okay, so the L2 is actually, would mean maybe, with L2, we would need less noise. And that's a trick we're going to use in the Gaussian mechanism. So the Gaussian mechanism will be based on the L2 sensitivity. And it means that for more dimensions than just 1, the scale of the noise will be smaller by some factor, which in general would be square root of dimensions. That's all important. Like it's an unimportant detail for now, but this is the reasoning behind as well. Why the Gaussian mechanism is also giving better utility, so to say, because there's less noise. So, okay, here's a refresher. And this, I mean, everybody should know this. I mean, this is something you really need to know by heart. In one or the other form, I use the form, the Gaussian distribution. So this is a density of a normal distribution or Gaussian distribution. And I use this form where it basically shows that, you know, if you have zero centered with with variance 1, then this simplifies to just you know, it simplifies pretty much to the standard normal distribution. And if you have mean, you shift basically to the left or right and divide by basically scaling this Laplace distribution. Okay, so excuse me, Gaussian distribution. So is everybody familiar with the Gaussian distribution? Okay. Okay. Was a famous book like the Little Prince? Is it a famous book? Little Prince? Okay, have you read it? How does it start? What is the chapter? The first chapter. Remember? Okay, so the young boy was trying to paint or draw a python eating an elephant, and he was drawing like that, and everybody thought like it's a head. And he said, no, it's a python, it's an elephant. Okay, so no, this is a Gaussian distribution. But anyway, actually it's a nice book. I mean, if you've never, I mean, it's kind of, it's cute, isn't it? Yeah. Anyway, so this is not like a python eating an elephant. This is a Gaussian distribution, very badly drawn, but you know, here's the mean, and this is somehow the, let's see. Okay. So you should know this for the rest of your life or anything else. Not the Python thing, but the Gaussian distribution. Okay, so the Gaussian mechanism. What do we need for that? So again, we have a numeric query which takes a database and produces a vector. Good. Then for any epsilon, now this is very important for this, what I'm showing later on, the epsilon cannot be bigger than 1. Okay, this is very important constraints for this kind of vanilla Gaussian mechanism. So epsilon should be small. Well, how small we don't know, but if they are big, this will break. So in this case, they should be smaller than 1. Otherwise, this will completely break. So for small epsilons and deltas, again, I mean, delta should be very small, of course, you know, 1 over n. The Gaussian mechanism takes the true answer and adds independent random draws from a Gaussian. And the parameter, you know, the parameter, the sigma square is, I think it could be equal or should be at least this value. Okay, so this looks awful, and I actually don't think we should remember that. I don't remember it either. But there are some, you know, if you remember the Laplace mechanism, the scale of the Laplace, just for comparison, the Laplace, we had a scale which was, I think it was delta over epsilon, as far as I remember. Yeah, it was Laplace as a scale delta over epsilon. Now we have delta squared over epsilon squared. Okay, this is interesting. And we have the delta here in this, and then some constants in there. So what does it mean? Yeah, it means that the scale of the, the scale basically of the distribution behaves a little bit differently for Gaussian than for the Laplace mechanism. So now it grows. Oh, okay, I can't think anymore, but there's a difference in this, you know, in the square thing. Anyway, so just once again, so if we have a query, for example, you know, the query would be a counting query, then in counting query, the delta to the sensitivity is how much is sensitivity for counting query. So how will the input be different if you remove one person and counting? I know it hurts, so try again. So it looked like you were thinking like very deep and like, oh, I can't. Oh, okay, sorry. So what is the sensitivity of counting query? If you have a database and counting people in the database and remove one person, what is the sensitivity? What is the maximum difference? Okay, it's 1. Yeah. What is the L2 sensitivity? Again, 1, because you know, we have just one dimension. Okay, so this is one, which means that we're gonna, given the epsilon, we're gonna plug it here and end up with sigma squared for the normal distribution. Then we get a true answer. So let's say the true answer is 50. And then we're gonna add a random draw from this Laplace, from this Gaussian, parameterized by delta and epsilons, and maybe we add something here, which is maybe 0.2. So we're gonna report 50.2. And this is going to be epsilon delta dp, right? Who's defining the epsilon and delta? We are defining epsilon delta. So this is a parameter everybody needs to agree before we just do this query. But this is the same as the Laplace mechanism. The true query plus random noise. Okay? Any questions? All right. So here we have, okay, well, I'm showing you the, I should have done another poll. So here's again, on the right-hand side, this is what we had before. So this is the Laplace mechanism where we have the true query value and the neighboring data sets. And this was the privacy loss random variable. So we saw like, oh yeah, this is bounded here with probability 1 and can't be more than this epsilon of 1. Can't be more. Okay. Now we see that if we draw the value for one data set and the neighboring data set and do the privacy loss random variable, we end up with a beautiful distribution, which is again Gaussian. This is a coincidence. This is not, as we saw, like not this is a coincidence for the Gaussian mechanism, but it doesn't hold for any other mechanisms. So this is very nice. So the privacy loss random variable for the Gaussian mechanism is again Gaussian. Ah, that's interesting. So, which means if you think about it now, I mean, here the privacy loss random variable was bounded from left and right like hard. And there was like, as we saw before, there's nothing here. There's no probability mass in here. While here in the Gaussian, if you think about it, okay, yeah, of course, it has tails. What are tails of the distribution? Like, these are the tails. So for example, you can say that, oh, okay, my epsilon will be bounded with probability of this, will be less than 2 plus minus, sorry, let me try again. So for example, if you have epsilon of 2, you can say, oh yeah, you know what? So I'll be here most of the time, but there is a chance that I will exceed 2. And you can exactly compute, how big the chance, I mean, this would be your delta. Like how big you are, what's the probability mass beyond your kind of ease. Okay, yeah, and we can do this. I mean, you can do this thing of establishing the delta, the sigma square. This is somehow an approximation, but theoretically you can do it even numerically by saying, well, I know the PDF of the Gaussian. I don't have a solution like a closed form solution, but I can always approximate the tail bounds here. So I can always somehow compute numerically what this is going to be, and this will give me my delta. So then I know how to make it happen, like reverse. Okay. So, and the Gaussian mechanism, as we saw before, this is epsilon delta differential private, right? Exactly for this reason. So the epsilon, with some probability, we will be bounded by epsilon from left and right because it's absolute value. And with some small probability, this is the tail probability, we will exceed it. Okay, and this is interesting. So let me just undo this ugly things. So again, there will be some, let's say, we have these epsilons bounded here. So there will be some probability we will exceed that. But what are the tails of Gaussian doing? Are they going to, as you go more on the side, they're exponentially decaying. Like this is exponential decay. So they're smaller and smaller exponentially. So the chance that the privacy loss will be high is getting smaller. The farther you get on the right-hand side, the smaller the delta is going to be, the smaller probability. Compare this to this case. We ended up with a non-trivial probability in infinity, or somewhere very bad. So this was super bad outcome with a super high variable. Well, with the Gaussian distribution, with the Gaussian privacy loss random variable, this is almost impossible, because this would be the Gaussian like that, which means, okay, yeah, most of the time you will be somewhere around here, but here the probability is so small, and even decaying, so you will never reach this. I mean, the probability will be like almost non-existent. So that's why the Gaussian mechanism is actually nice. I mean, yeah, you can cross the line and you can be worse than epsilon, but this is going to be lower and lower exponentially, right? I mean, exponentially. Why? Because of this exp and this squared, like it's going down very fast. Gaussian has like very light tails, so to say, right? If you compare this with the Laplace, excuse me, just come back. The Laplace distribution, it's also known like has heavy tails, because it goes down with exp minus x is the Laplace, right? So it's exponential and going down exponential, while Gaussian is going minus x squared. Like that, it's a difference, right? Very substantial. So good. So this is why the why the Gaussian mechanism is actually it's breaking epsilon in a way. I mean, it's getting somewhere, but the consequences are not so bad, because it won't be that bad. You will break with delta, you will break this epsilon boundaries, but the chance the outcome will be super bad are super low. Okay, so this is why it makes it kind of interesting for practical applications as well. Any questions on that? Awesome. We should finish with a couple of general properties of DP algorithms, which we haven't talked yet before, because it makes sense to introduce them when we already know epsilon delta differential privacy. So they will hold also, everything which holds for epsilon delta differential privacy will hold for epsilon zero differential privacy. So the one thing, and we kind of assume it all the way down before, is the post-processing. So if we have a epsilon delta differential private algorithm, and we use any function on top of that, on the output will be again epsilon delta differential private, right? So we have a, I don't know, we have a counting query. I'm sorry, I should write that people can read it. Counting query. Then we have a Laplace mechanism, and it gives us some output. So for example, some very ugly number, like I'm counting persons, and the result will be 51.72. So what I'm gonna do, I'm just gonna round this to 52. And I'll just give you this value. So if this is epsilon delta dp, this is also epsilon delta dp. So I cannot undo the privacy by applying any, so this is like rounding, for example. Yeah, so you can apply the mechanism, which gives you a real number, and you can round it or multiply by 2. Whatever you do, you cannot undo this. I'm not showing the proof, you can look it up in the book, but it's kind of also intuitive. Like, you cannot like make it weaker. You cannot weaken privacy by anything what you do on top of it, because you can make it stronger by applying some other mechanism or whatever, or making more random somehow, but you cannot make it weaker. And this is great. Why? Well, no matter what you do, like if you see the output of differential private mechanism, which was truly differential private, even if you have like quantum computers or whatever, you cannot undo the privacy. It's theoretically impossible, right? So if you, for example, publish your data under differential privacy to the world, nothing on the world can undo it or make it weaker. Nothing, unless there's unless there's another access to the database or anything like, but mathematically you cannot undo differential privacy or make it weaker. This is a very nice property, like even the most essential. So it's basically future-proof forever. if you do it right. If somebody steals your, random number generator, that's a different story, But formally, theoretically, it's bulletproof. Good. We have something also called group privacy, which is, well, we had neighboring data sets D and D prime, and they previously differed in one position, right? So we have just one person different or one removed. So we can also have a group of people. So we want to protect a group of people. So these databases differ in k positions. Excuse me. And we have a mechanism which is epsilon delta differential private. Then with these k positions, this mechanism will have these guarantees. So what is going to change is that we basically multiply the epsilon by number of size of the group, so by the k, and there is some multiplicator here for the deltas as well. Okay, so if k is 1, then we're going back to the baseline, sort of like e to the power of epsilon, and here this would be what's this? E to this 1 k times delta. No, even like 1 times delta. So this is delta. Okay, so if k is 1, this is the standard what we saw before, and with k more than 1, then there's like multiplication. What does it mean? Like for large groups, this gets very, very big. So that's what you don't want to do it. Like for k should be small. And that's why most of people like work with the standard kind of single person neighboring data sets. Okay, so then it behaves nicely. But you can theoretically do group privacy. But actually I don't see it happening for NLP or machine learning. Everybody's working with the standard notion of neighboring data sets. But I just wanted to mention that it's like an interesting property. And the last one is the composition. Okay, and now we're finally revealing why we call this thing privacy budget. Okay, so let's have a k mechanisms or algorithms, and these are in sequence, and each of those mi's is epsilon delta differential private, and these epsilon i's and delta i's could be different. So there could be one. So m1, for example, could be, I don't know, 0.5 and 0.0001 dp, and the second could be like 2 and 0.001 dp. Okay, so we would have like 2 mechanisms, and they actually might be, so the output of one mechanism could be they can adapt. For example, given the output, maybe I decide something else. So this is not something that you decide upfront, but then they can basically adapt. So the whole thing then is basically summing up the epsilons and deltas. So this would be then what? 2.5 and 0.0011 dp. This is nice. Yeah, so that's why it's called a budget, because you can spend it for a sequence of private queries. Well, if epsilon is delta, then it's easy. So then you just split, the epsilons. And if you have deltas as well, you can sum them up as well. So you can basically now, okay, the composition is interesting. Why would we do that? Well, imagine you have really a database of patients. And of course, you don't want to ask just one single query. You might be interested in more queries, right? Oh yeah, okay. So then you have to take this composition into account. And well, this basic composition is actually pretty bad in a way. And there are better, why bad? What does it mean bad? Well, this, with number of queries, this gets high. And it can get so high, then you say like, well, it's not private anymore. If you have like 100 queries, and each of them is 0.5, with 100 queries, you end up with what? You would end up with total epsilon of 50. Okay, so I would say like total epsilon of 50 is non-private at all. Why? Remember randomized response, coin flipping. the epsilon was logarithm 3, like 1.2 something, 2 point, let's give me that 1.2 something. So, and this is something like acceptable. Epsilon of 50, what would it mean? Like that most of the time you would just tell me the true answer. Okay. So there are better composition mechanisms that actually allow us to do like 100 queries or 10 queries while keeping the overall budget somehow meaningless. Okay. But in general case, yeah, you just sum it up. So if I give you a database and you have like 100 Laplace queries, like 100 queries, then you have to kind of, for each query, you are spending some budget. Maybe I'll tell you, okay, well, you can ask queries for epsilon of 5. So think wisely what you're going to ask. Maybe, not. And why is that so? I mean, of course, with each query, you're learning something about a database. So everything has to be privatized and everything has to sum up. This is also why we have e to the epsilon here in the, so we have e to the epsilon. Because if you multiply e to the epsilon a couple of times, you're just summing up these epsilons, right? So this is the reason why you're summing up the budget. Okay, so this was the basic composition, and I guess we're kind of finished more or less on time, I guess. Maybe it was too quick in some parts, but I don't know, you have to tell me. Any questions so far? So I can just summarize quickly why is today lecture interesting, or why is it useful at all? So we have pure differential privacy epsilon 0, but we say like maybe sometimes we can have mechanisms where we sacrifice a little bit of privacy for much better utility in multiple dimensions. So if the query is multiple dimensions, then the L1 norm is kind of killing us. There's a lot of noise, and the results are going to be bad, or the utility is kind of heavily impacted by that negatively. So we're gonna sacrifice a little bit, tiny little delta, which is even less than 1 over n. But for this tiny little delta, we might get mechanisms which kind of behave nicely, such as this thing, where even if we kind of get epsilons larger than what we want, probability of them will be smaller and smaller and smaller. But for that price, we get some nice properties of this mechanism. So Gaussian mechanism is interesting because many things in nature are Gaussians. For example, we're going to use this for training neural networks. And I guess we're going to do this next lecture already. So, okay, finally getting together all these things like compositional things and the Gaussian mechanism for training deep learning models, where this Gaussian mechanism takes place. If you try this with pure differential privacy like Laplace, you will get super high epsilons for some utility or something which is completely rubbish, like the model will not work. With Gaussian mechanisms, you will get somewhere. What you're kind of paying price, yeah, well, there's delta. Delta, in some cases, had bad consequences, as we saw with, I'll give you the whole database, but in practice, we don't use these algorithms. This was like stupid algorithm with, very badly designed, which was still epsilon delta differential private, but not really well behaved. The Gaussian mechanism is super well behaving. And that's it for today's lecture. Thank you.